Today's topic is going to be fossils. And that's one of the most fun things that you get to do in historical geology is study fossils and understand what they tell us about Earth's history and just how amazing life on Earth is. And today's just going to be an introduction to that. As we go further in the semester, we'll be taking a look in detail at different organisms that lived in different time periods. Now, here are some terms to know as we start studying fossils. Well, today, when we use the term fossil, it means any evidence of past life. And it didn't always mean that. If we go back in time to like the Renaissance or the Middle Ages, fossil kind of referred to anything neat that you would dig out of the ground, anything that had a weird shape or looked cool. But today, it means evidence of past life. Now, when we describe organisms that are alive today or were alive in the past, we might use the term cosmopolitan. This means we're talking about a species that's very widespread and not restricted to a specific location. So you could say that, like Homo sapiens, our species is very cosmopolitan, right? We live all over the world. Now, for organisms that are not that way, we use the term endemic. And this is species that's confined to a very specific area. So, for example, there's a certain type of bird that only lives in the Galapagos Islands. And, well, we would say that bird is endemic to those islands. It's limited to those. And my cat has allergies, so you probably hear the poor little guy sneezing. You okay, little fella? Okay. All right, now when we study how fossils are created, this is called taphonomy. Taphonomy is the study of how organisms become fossilized. And it's something you can actually specialize in. You can look at, well, when you know a shelled organism dies, how does that shell end up getting preserved for us to then see millions of years later? Well, there's a few things that help organisms become a fossil. Possession of hard parts. If something is just soft and squishy, like a jellyfish or so, it's not as easy to preserve. I'm not saying they can't be preserved, but it's harder for something that's just soft and squishy to be preserved. So having hard parts like a shell or bones or teeth really helps. Also, rapid burial. The faster that this deceased organism can get buried, the better its chances of being preserved as a fossil. In rapid burial, what it does is it isolates it from scavengers, so you don't get things like buzzards picking the thing apart. You isolate it from aerobic bacteria. And aerobic bacteria, aerobic means in the presence of oxygen, and these bacteria decay the organism. And if we bury it, we basically then remove it from those bacteria that will try to decay that. And in this rapid burial, the sediment that has buried that might seal off the organism from chemical fluids that would help decompose the organic matter as well. So the two big things to help something become a fossil is having hard parts and rapid burial. Now, soft tissues can get preserved, but like I said, it's not as common. And one thing I would like to add, the finer grained the sediment that is burying the fossil, typically the more exquisite the preservation. So really fine-grained sediments can preserve lots and lots of detail in the fossils that get buried. All right, so let's look at some of the types of fossilization that can occur. You can have unaltered parts. And in hard parts, well, some skeletal material is quite stable. And a great example is calcite. There are many organisms that have created shells out of calcite. Calcite is an extremely stable mineral over time. And so you'll have these shells made from calcite, and that's exactly the substance that they were when that organism was alive. So that's unaltered. Now, you can get unaltered soft parts, but that's a lot harder to preserve. So you might get in ice preserving soft parts. And for example, this is a 36,000-year-old steppe bison that was trapped in permafrost. Basically, it had fallen in somewhere in the Arctic, and permafrost ice surrounded this organism and preserved it, so you can still see the skin and the hair and things on there. And so ice can preserve soft parts. Amber can as well. What we're looking at here, amber is fossilized tree sap, basically. And see this thing right in there? That is the tail feathers of a juvenile Coelurosaur, which might not mean much for you, but that's the group of dinosaurs that includes raptors. So what you're seeing right there is a raptor feather. And we also have an ant. But in any case, amber can preserve these soft parts. And then in bogs, because you have stagnant water, you can get soft parts being preserved as well, as we see in Tollandman here, who he died around 350 BC, but the preservation is still so good that you can actually see like the hair on his chin and stuff. So you can get soft parts being preserved, but you do need special circumstances for that. All right, now we can also have altered parts. And that means that the fossil somehow has changed from its original composition. So for example, you can have recrystallization occurring. And in this case, the original skeletal material gets changed into a new mineral or maybe larger crystals of some kind. And in this case, no material is added or removed. And the example is aragonite to calcite. So both aragonite and calcite are calcium carbonate. And so they have exactly the same chemical composition, it's just the crystal structure is a little bit different. And so you might have an organism that originally had an aragonite shell. Well, that shell material will recrystallize into the more stable calcite. And so that would be an example of this recrystallization. When things get altered, you also might have something called permineralization occur. And this is the addition of material to fill the pore space of a substance. Now, pore space is open space. And there's two substances especially that have a lot of pore space in them. Wood is one of them. The other is bone. And so bone and wood often gets permineralized because what happens is these like groundwater can be flowing through the area where your tree or your bones were buried, and the groundwater will then precipitate minerals in all of the pore spaces, thus preserving that, that fossil. Now, in addition to other types of altered parts, you can have replacement. Replacement is where the original skeletal material gets removed and then a new mineral replaces it. And our example we have here, this is a type of organism called a brachiopod. It would originally have a calcite shell like this. And in this one, it's being replaced by the mineral pyrite. And so totally different chemical composition. Calcite is calcium carbonate, pyrite is iron sulfide. So we completely removed the original and replaced it with a different mineral. That's replacement. And then in fossilization, you can have what are called molds and casts. So a mold is skeletal material gets dissolved, leaving an open space. And that's what we see here in this top diagram. We have this shell gets buried, and then it gets dissolved, leaving an open space in the rock. And we can then, like maybe when we're breaking the rock apart or so, we will end up finding that open space in the shape of that particular shell. Now a cast is where we get a replica of the original when a mold gets filled. So we have the shell buried, it gets dissolved, we have this open space there, but then sediment or some other mineral will come in and fill up that open space, and that's going to be the cast. It gives us a replica of the original fossil, but it is not the original fossil. It's made out of some other substance. Then we also have carbonization. And carbonization is where the organism is preserved as a thin film of carbon. And I couldn't resist putting a little Star Wars reference in there. But really, carbonization looks a lot like this. So here we had a leaf. And remember, organic material is made of a lot of carbon. And when that leaf got squished in between these layers of rock, basically it left this thin film of carbon showing us the remains of that organism. Now, all the previous types of fossilization were what we call body fossils. These are where some sort of actual piece of an organism is preserved. It was like an impression of the leaf, or it was a shell, or it was a bone, or a tree trunk. Well, we can also have what are called trace fossils. And trace fossils are indirect evidence of past life. Things like tracks. Right? We have this trackway of a dinosaur called Acrocanthosaurus. Trails that are left by organisms, or places where they've burrowed into the ground. Those all count as trace fossils. Also, coprolites. Coprolites are fossilized dung, fossilized poop. This is a coprolite of a plant-eating dinosaur from the Jurassic. So it's not an actual piece of that organism, but it is definitely something that it left behind. Trace fossils can also be things like gastroliths. So some dinosaurs would actually ingest little rocks. And those rocks would sit in a stomach or a crop and help grind up the food. And that's what we're seeing right there. Those are gastroliths. And they're not an actual piece of the organism, but it was a part of the organism that it left behind. And then there are feeding traces. So we have these shells right here, and then we have this. That is a drill hole made by a predatory snail. That's the shell of the predatory snail. It comes up to this organism, it drills a hole in there, and then it eats the organism. And so even though the snail didn't leave a piece of its body there, it left evidence of itself there. And that counts as a trace fossil. All right, so now we've seen how fossils can be preserved in many, many different ways. And one of the things that's very important in historical geology is figuring out when things happened. Right? We like to know the timing of things. And something that can help us with that are index fossils. Index fossils are organisms that were abundant. They're cosmopolitan. They lived all over the place. They're easy to identify, and they only lived for a short time. So it's a certain species that only lived for this short time period. So wherever we find that species in the world, when we find it, we know we are looking at rocks from that specific time. And so this can be very useful when we're correlating rocks from different parts of the world. All right, so in this concept of using fossils to help figure out when things happened, we have to know a little bit about what's called biostratigraphy, or biozones. Well, bio means life, and stratigraphy is looking at the layers of rock, so biostratigraphy is looking at the life in the layers of rock. And we can have what's called a range zone. And these are strata, and remember strata just means layers of rock. These are the layers of rock representing total geologic lifespan of a taxon. And a taxon is, well, any group of organisms. So it might be a genus or a species of organisms. And then we also have the concept of what's called a concurrent range zone. And these are the layers of rock characterized by the overlapping range of 2 or more taxa. So what I have right here, let's say, here's my time periods, right? Cambrian, Ordovician, Silurian, so on. Let's say I have one fossil right here. That's its range zone. It shows up here, and that organism, that species, lives all the way to up here. Or over here, this is a different fossil. It shows up there, and that species lives all the way to there. So this whole time period is the range zone of that fossil, or this whole time period is the range zone of that one. The concurrent range zone is between these red dotted lines, right? Because that's where those two fossils, that's the time period during which those two coexisted. And so we can then look at things like that, seeing where, if we find a rock with multiple fossils in it, we can figure out when did all of those organisms coexist, and that must be when our rock was created. You'll also sometimes see something called an assemblage zone, and these are rock layers characterized by a group of organisms that lived in a particular environment, and this doesn't really pay attention to time ranges, and I just wanted to put that in there because you might see that in your book, and I just want you to be aware of what that is. So how can we ultimately use fossils and mesh that together with numerical dating to figure out when things occurred? Well, let's say over here, this is my stratigraphic section, and I'm lucky enough at this section to have granite that's dated at 480 million years old and a lava flow dated to 450 million years old. And right here I have these two species. Well, I know since that rock is between those two, it must be the age of that between 450 and 480 million years old. Then if I go over here I have no igneous rocks that I can get the numerical ages on. But I have those fossils, and I know those fossils lived between 450 and 480 million years. So I have a good idea that that rock formed in that time period. So you can actually put together numerical dates and some of your index fossils to get a nice view of when different events happened on Earth. All right, so a part of studying biology is called ecology. And ecology is the study of relationships among organisms to each other and to their physical environment. And in historical geology, we spend a bit of time studying paleoecology, right? Ancient ecology, because we get all of these different fossils, and we can then start taking a look at how those organisms related to each other and what their environment was like. So I'm going to introduce some concepts of ecosystems that we will be talking about throughout the semester. And today I'm going to be introducing marine ecosystems. And when I do this today, because hey, Earth has like what, 70% of the planet's covered by water, so we've got a lot of rocks that were created in water, and so it's important to know a little bit about the ecosystems and the organisms that lived in those marine areas. All right, so when we talk about marine ecosystems, we have pelagic. And this describes all the water above the seafloor. So if I say something is a pelagic organism, it means it lived somewhere in the water above the seafloor. benthic means it lives on the sea floor. Now, in the pelagic ecosystems, we have the neritic zone, which is above the continental shelf. And remember from physical geology, the continental shelf is that area of shallow water right next to the continents. And the water is usually less than 200 meters deep there. What this means is that the photic zone goes all the way to the bottom, of the sea at that location. And the photic zone is where light can penetrate water. If you go into the deepest parts of the ocean, light doesn't penetrate there. It is pitch black. But here in this neritic zone, you're going to have light penetrating that water. The oceanic zone, well, that is seaward from the continental shelf, and that's the deeper water where it's going to be pitch black out there.